Good evening. For those of you who I've not met before, my name is Richard Barnett, and I have the honour and pleasure of being Vice-Chancellor of Ulster University, and I'm absolutely delighted to join you this evening and have this opportunity to welcome you to Ulster University and to the Belfast campus of the university, and of course to the 2014 IrISS annual lecture. The purpose of the annual lecture is to contribute to public debate about contemporary issues in the social sciences, and for our research and associated research to reach out beyond the academy and beyond the university. And we do this by inviting internationally distinguished researchers to deliver the lecture, internationally distinguished researchers whose research relates to research being carried out in part of IrISS, so it's related to our research as well. So in short, this annual lecture is about research that is firmly grounded in theory and is applicable. And that epitomises what the work of IrISS is about, but it not only epitomises what the work of IrISS is about, it epitomises what the research, the centre of gravity of research at the Ulster University is about. Our centre of gravity, as I say, is about applicability rooted in rigorous theory. And this relates to the raison d'etre for this university. Our purpose is clear, it's unambiguous. It is to work in partnership to promote economic, social and cultural development. But that is not enough for us. At this university, it is also about promoting economic, social and cultural inclusion. For us, development and inclusion must go hand in hand, and much of the research in IrISS and elsewhere in the university is about that combination of inclusiveness and development, and it's the theme of the topic of this evening's lecture. And as I say, that work and that idea of that nature of that work permeates the four principal strands of IrISS. I keep saying IrISS. I'm assuming you all know who IrISS is. She's a very well-known individual, a person, our Institute for Research in the Social Sciences, and the four strands: social policy, very broadly defined, politics, education, and of course linguistics. And it also permeates the work of other research centres in the Faculty of Social Sciences, very strong Faculty of Social Sciences at the university in terms of teaching, in terms of the research. So for example, in terms of the work in our Transitional Justice Institute, the other research centre in the faculty, and later this week I have the honour of opening a conference there on human rights and dealing with the past, again, which epitomises also what IrISS does and what TJI does. It's about applicable research, research that will contribute to policy, but also research that is willing to challenge. And that's what universities must be about, and that's what the University of Ulster is about, the willingness to challenge and challenge policymakers. And of course, we're delighted that the faculty also is home to INCOR, our United Nations affiliated centre on peace and conflict. In a moment, IrISS's distinguished director, Professor Cathy Gormley-Heenan, will introduce this evening's speaker, Professor Laura Ann Petito. Can I, on behalf of all of us, Laura Ann, say how delighted and honoured we are that you're able to join us this evening, and we're looking forward to your lecture. Your work in particular, as you will know, relates to the work being carried out in the Ulster Centre on Multilingualism, led by Dr. Rafi Foley, and which aims to educate and inform the public about the benefits and advantages of bringing up children to be multilingual. I have to say, and I hope I have a personal interest in this because I have a fascination with the whole topic, because my brother's wife, so my sister-in-law, is Italian, and their two children, when they brought up, they were jabbering away 1 minute in English and 1 minute in Italian, and I just didn't know how their brain worked and how they knew that 8 was Otto, but they seemed to without being told. So and it's, anyway, it's fascinating, and perhaps I'll learn more. I always thought, when I retire, I was going to study something that would allow me to find out how that works. And of course, but more generally, that is all related to policy issues here in the North. With our language strategy, the language strategy developed here, there's contributions again by staff from the university, which is looking at the cognitive development for language in children, but also the economic and cultural importance of language and multilingualism and the recognition of that. So once again, I'm absolutely delighted to welcome you all to this annual IrISS lecture and join with you in welcoming Professor Petito, and like you, I look forward to this evening's lecture. And I would now ask IrISS's director, Professor Kathy Gormley-Heenan, to introduce formally Professor Laura Ann Petito. Kathy.
Thank you, everyone. You're very welcome this evening. Professor Laura Ann Petito is, despite being a world-leading expert in cognitive neuroscience, is also a very modest person, and perhaps won't be best pleased if I introduce her with the sheer volume of awards and expertise and distinguished accomplishments that she's had. But I'm sorry, Laura Ann, I'm going to do it anyway. Professor Laura Ann Petito is a cognitive neuroscientist, and she's the principal investigator and the science director of the USA's National Science Foundation's Science of Learning Center, which looks at visual language and visual learning, and that's at Gallaudet University. As well as that, she's a full professor of psychology at Georgetown University, and she's the scientific director of her own brain and language laboratory for neuroimaging. She's well known for her role in the creation of the new discipline, educational neuroscience, and I've just been informed that she was actually invited by the Pope to the Vatican to discuss some of that new disciplinary understanding. And she's one of the co-founders, as well as the chair of the steering committee of the PhD in Educational Neuroscience program at Gallaudet University. And this is the first program of its kind in the United States, and certainly something that is world-leading. She's renowned for her scientific discoveries concerning language and its neural representation in the human brain, particularly how young children acquire language, the shared signs and spoken language processing sites and systems in the human brain, the bilingual brain, including sign and spoken bilinguals, and the reading brain, including how young children use signing as a visual display. She received her master's degree and her doctoral degrees from Harvard University's Graduate School of Education. She's won many federal and/or foundational funding awards over the past 30 years, and we look forward to hearing how you've had so much success with that. We could take many tips from you, I'm sure. She's the recipient of over 35 international prizes and awards for her scientific achievements and discoveries, including the 1998 Guggenheim Award for what was known as, and this is a quote, her unusually distinguished achievements in the past and her exceptional promise for future accomplishments in the neurosciences. In 2009, she was appointed a Fellow of the American Association for the Advancement of Science, and she's also a Fellow of the Association of Psychological Sciences. Laura Ann may well be a very modest professor, but she's certainly a world-leading expert in her field, and we're very delighted to have her here this evening to deliver the 2014 IrISS Annual Lecture. Thank you, Laura.
Right. Your linguistics department is world-renowned. Your Center for Multilingualism is world-renowned. The moment I got the invitation, I was thrilled and honored and felt I can't wait to go there. Who does bilingual research and doesn't know about your accomplishments? I especially want to thank Dr. Gormley-Heenan for the introduction and for inviting me, Dr. Raffaele Folli, for being so incredible in this invitation and taking much time to devote to me and to have let me see your beautiful Belfast, and also Professor Hugh McKenna. So what I'd like to do today is to share my passion for human language. I knew I was fascinated in human language since I was age 11. I didn't know the field I would end up in. Cognitive neuroscience didn't exist at that time. But I was fascinated in the properties of human language, in particular its complexity. And I was especially interested at the time in the problem of epistemological problems, like where does knowledge come from? And what fascinated me was the mismatch between the nature of the signal and what our brains do with the information. So for example, there are many ways in which we encode human thought. It could be through smells or touch. But I think many would agree that one of the quintessential forms of the encoding of thought is through human language. And I was fascinated in the fact that the signal is so complex, and yet if you open the brain, you wouldn't find anything that looked like what I was saying. So for example, when you have the impression that I'm saying words, and when you see what I'm really saying, it's spindles of air that are going through the air, that are hitting your ears, that are turned into neurochemical activity. So the relationship between the neurochemical activity and the words is very remote. That neurochemical activity then moves up the basilar membrane, is dumped into a tissue called Heschel's gyrus, which is your primary auditory cortex. From there, it moves into your secondary auditory cortex. Then it goes up the stream to various other brain systems, and in milliseconds you have the sensation of hearing meaning. So the question is, given this incredibly complex signal and a complex way in which our system encodes and makes sense of this signal, how is it that our species learns it? How does it happen so quickly? So for example, we all know that a child's born at about, when the child's born, as intelligent as we think our children are, I think everyone would agree that your child wasn't speaking full sentences at birth and didn't know definite words at birth. However, at 12 months, we start to see a difference. Children are beginning to comprehend simple sentences. They've already begun their first word. A typically developing child already has the phonological inventory of their native language. They have rudimentary gestures. They can signal intention and desires. And so there's a very rapid way in which children begin to get the basic information of human language. And the question is, how does that miracle happen? The computations that a child passes through to get from the signal in the world and the representation of meaning is said to be one of the most complex computations that we know of in the universe. This is a very complex interaction between biological systems and what the child's born with. And so my interest has been, how does that happen? This is a visual representation of the signal of what it would look like if I was speaking through a speech spectrogram now, just spindles of air. From those spindles of air, the young child is going to extract out little bite-sized chunks of their phonological inventory, from which they will then build all the words and meanings and sentences in their life, in their language, and for the rest of their life. And in early life, it's the system on which they draw to begin to decode from the sound to the letter en route to meaning. And all members of our species use sound or phonological information to decode from reading, even writing systems that don't have an alphabetic base. In the early stages, the importance of a phonological decoding in early reading is invaluable. So my question has been, how does this happen? So I'll give you two of the answers now before I get to the end of the talk, just so you know where I'm going. Through many decades of work, these are representative samples of my own publications. The conclusion is that the human child is born with select tissue in the human brain. It's particularly located in the superior temporal gyrus. And this tissue is sensitive to highly specific rhythmic temporal patterns in the input that have to be in maximal alternations of about a hertz. And this is the machine that allows the child to find in this sweet stream and swish of sounds the bite-sized unit of early words from which they'll build their phonology. You can imagine it as this swish of multiple types of stimulation, and the child has to immediately begin to break it into parts. And this is the tissue that allows the child to break that into parts, to find the phonological unit in the first place. This is the same tissue that is going to be at work when I discuss bilingual children and bilingual acquisition. This is the tissue that allows a child to begin learning multiple languages and not be confused, because the child sets up these early bins of language based on rhythmic temporal patterning, even blind to meaning. The initial way in which a child's going to begin to differentiate their multiple languages is going to be through a phonological map into the language. Another thing that's very important about human language is that the child has to be exposed to these patterns very early in life. We also know that the child can't simply be exposed to the patterns like through a television, but the child needs to have social interaction. And that is part of our species. This is a very important species-specific type of cognitive transfer that we do. And finally, if the child has the sensitivity to the patterns and has experience with patterns in the environment early in life in socially contingent ways, this is something that facilitates the child's learning of language for the rest of their lives. But let's start back in a moment. First, I'm going to let me give you the plan of how I'm going to divide the information up today. That's what we now know as scientists of how a child's going to get into the human language acquisition process. But to take you with me and to help you see how we arrived at this conclusion, first, we're going to talk about what makes language special and some of the early experiments that I was involved in which I asked that question. Then there was going to be new information that came from those series of experiments, and then I'll segue into part two, in which I'll direct specifically bilingualism. And finally, I'm going to turn to the bilingual brain. These earliest studies will involve, particularly with bilingualism, largely behavioral data, but then I'll segue into the bilingual brain. So to begin with, in asking what makes language special, I first began doing this at Columbia University. This was a very serious scientific project in which we attempted to teach sign language to an infant chimpanzee. The question was whether all aspects of human language were entirely teachable or learnable through environmental input. Maybe human language is just totally taught. Maybe we take our children and we speak to them often, and they, through learning and reinforcement and contingency into imitation, maybe a child just learns language that way. So if that were true, then we should be able to take a chimpanzee and simply raise it like a child in a rich and loving and communicative and socially interactive way, and the chimpanzee should be able to learn language just like a human child. Well, while you know these are very, very controversial experiments, but all parties agree that chimpanzees fail to master key aspects of human language. This is uncontroversial. They fail to master key aspects of human language. And so why do they fail to master key aspects of human language? The field at the time, and even now, offered a prevailing hypothesis. And the hypothesis was that chimpanzees fail to communicate the full complex of human language because they cannot talk. And the prevailing hypothesis was that speech was special. And so we did know neuroanatomically and physiologically chimpanzees cannot produce human speech because they do not have the vocal tract that humans do. However, what was I using in the videotape? Sign language. Well, sign language was hoped to be a medium that we can use to trick the brain and bypass the brain and get into it, give the chimpanzee language through the hands. So if the brain was the center of language and all language was teachable, then the chimpanzee should just learn the aspects of human language the way a child does. But it didn't. Even though we gave the chimpanzee a medium to bypass his inability to talk, he nonetheless did not out all of human language. Nonetheless, there were things that he couldn't learn. So that raised a hypothesis that something else must be special about human language. Segueing into human language, there was this prevailing view that speech was special. But after seeing the fact that we gave the chimpanzee sign language and he still didn't out it, it made me question whether it was speech that was special in human language or whether there was something else. So I turned to testing it. The first group of studies were going to be a test of the hypothesis. Is speech special to human language acquisition, or is there something else that's special? I mean, clearly we're trying to get closer and closer to what is special. So how might you study that? One way you can study that is just simply compare children acquiring spoken language and children acquiring signed languages. If speech is special, and we need speech to develop the maturational timetables that we see, and we need speech to develop the capacity to understand language, then if you take the human brain and you strip it of speech and you give it instead the hands, then you should mess up the acquisition process. The child who's exposed to sign language should learn language in a different way. The pattern could be early, the pattern could be later, but the language acquisition course should be different. And what did we find? No, when you compared children exposed to spoken language and children exposed to sign language, the children achieve each and every milestone on the identical timetable. So if you're exposed to sign language, you begin babbling by 10 months. But if you're exposed to spoken language, you begin babbling by around 10 months. Children exposed to sign hit their first word milestone at 12 months, and children exposed to spoken language hit their first word milestone at 12 months, and so on and so forth, up the developmental scale. Milestone for milestone, grammatical analysis and process, grammatical changes, morphological analyses, then to syntactic analyses, types of sentences and relative clauses and negation, all the components that we knew to exist on a maturational timetable in spoken language was seen on the identical timetable and sign language. So that raised the hypothesis that perhaps speech was not special. Whatever it was in the brain that was controlling the maturational milestones that we see in language acquisition existed in addition to our capacity to talk. Something else, whatever it was so powerful that the brain could look at these two radically different modalities and converge and see the structural invariances across these two modalities. So the question was, how robust would this be? So then we turned to bilingual children, and this was going to be a special type of bilingual children, again, to test the speech is special hypothesis. And these were children who were hearing children raised in bilingual homes. The bilingual home, though, was going to be a deaf mother who signs and a hearing father who speaks. So we were playing with the we were manipulating the modality that children were exposed to. So if speech is special, and if 350,000 years of phylogenetic history was on this child's shoulders in ontogeny, we would expect this young hearing child in a signing and spoken home to, let's say, turn away from sign and try to glean any morsel of sound it could get. We would expect the child in development to show us an asynchrony in the development between sign and speech. We would expect the children to favor speech over sign, if it was speech that was special in language acquisition, not the patterns that get pressed into speech or sign. So we would expect the children to show us some type of asynchrony, and instead what we found was the children in these studies achieved, these were bilingual children hearing in signing, speaking homes, achieved each and every milestone on the identical timetable. So if they hit the first milestone in babbling and sign, they began babbling and speech. If they hit the first word milestone in sign, they began saying their first word in spoken language. So here's an example of one child. I'll let this little clip speak for itself.
Simon is almost 2 years old. He's signing. And he's speaking. His mother is profoundly deaf and signs to him. His father is partially deaf and speaks to him in French. Simon, who has normal hearing, seems perfectly comfortable with this arrangement.
These children were compared to hearing children learning 2 spoken languages, many different pairs. These are many studies. This is really 20 years of work. I'm summarizing very briefly now. And what we find is that the children acquired signed or spoken language equally. Again, whatever it is that's controlling the acquisition of sign must also be controlling the acquisition of speech. And it's not and it's something that is perceiving the structural invariances across these 2 modalities. So now I'm going to turn to the last group in this particular trilogy of studies. To further test the hypothesis, was speech special? I will show you a rather extraordinary group of children. These are children who were raised in rural Quebec. The children were entirely normally hearing, and in Quebec, language is very politicized, and it's very politicized whether you're hearing or deaf. These were French deaf families of a francophone cultural background, and their view was quite strong. My child, I'm deaf, I sign LSQ, langue signe québécoise. My child's going to be exposed to it, and when it goes to school, it'll get the other language. I had English ASL families who said culturally English but deaf families with hearing children. My child signs, we sign American Sign Language here. My child is going to learn ASL. And I also had French families who spoke French who said, my child's going to learn French and one day they'll learn English some other time. So this was a normal cultural environment, and so you will see, I'm about to show you what happens to the children who are entirely normally hearing but getting no spoken language input. Now, if speech is special, if it's speech that's the biologically required component to learn human language, what should happen to these children? They can hear. Speech is being denied from them completely. There's no systematic language spoken to them. Clearly, if the mother pulls up in the gas station, the child might overhear the gas station attendant say, "Do you want gas?" But we know that children don't learn language that way. They need systematic exposure. These are hearing children in their home who've had no spoken language up to age 3 and age 4. These children achieve every single milestone in human language on the identical timetable. Every component that you study in linguistics, as I said, first words, 2 words, morphological markings, syntactic markings, question formation, negation, etc., etc., etc. So I'll show you one of these. This is an 18-month-old child. All of you have children. This is a typical 18-month-old child. We're in a naming and context. The woman, this is the hearing child. It's a name. What is this? That's a washcloth. Yes. That's a washcloth. Yes. That's the mother over here on your right, on my right. Yes. That looks to mom for confirmation. That's a brush. Yes. And knows what the function is that you do with the object. So this child is now quadrilingual. She's an older now. She speaks French, English, ASL, and LSQ. I should just say that sign languages are not universal. There are different sign languages signed in all in different countries, and they're not the signed counterpart of the majority spoken language. So these are naturally evolved languages, and this is normal timetable. So having seen the overarching timetable of human language be identical across the modalities, we concluded that speech was not special, that there's something in the human brain that is able to perceive structural invariance across the two modalities, and that structural invariance must be something about the rhythmic temporal patterning of human language that is beyond modality, something well beyond that. So now, having seen the overarching timetable, now we'll take the beacon and we'll shine it into the very earliest onset of human language production. Obviously not perception, children can hear in utero, but it's language production. Universally, human babbling, when the child begins to babble, canonical babbling, rhythmic undulating patterns of ba, 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 da, 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 and the more advanced babbling, abba, variegated babbling. Linguists have universally regarded that as the onset of language production. In other words, we understand this behavior to be fundamentally linked to linguistic behavior, language. So now, the one problem is that babbling is thought to be a product of the orofacial region. It's thought to be a product of speech. It's thought that the child, actually human children do not have a human vocal tract until around 4 to 6 months. They're born with an animal vocal tract at a curve. At around 6 months, the larynx connects to the back of the nasal passage, and the human vocal tract goes into right angles. The child's jaw can drop. Phonation comes out, and we think we see syllables, ba, 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 da, da, da. But the origin of that capacity is said to be universally part of the maturation of the orofacial region. So now, having said that, all parties agreed that seeing babbling in young deaf children who sign is impossible. Why should it be impossible? Because their language doesn't involve the mouth. Their language involves the hands. So how could they possibly babble if there is no development of phonation, there is no use of their mouth? They're just using their hands. And actually what we discovered is that deaf children exposed to sign language babble on their hands. This is the first discovery that appeared in Science in 1991. These children produce rhythmic hand movements in maximal contrast, similar to a syllable. Open, close, open, close, open, close, open, close, open, close. A rhythmic opening, closing of the hands. So at first, when we saw this, one hypothesis was maybe this really isn't linguistically relevant. Maybe it's not babbling. Maybe it's just deaf children are exposed to sign language and they just do more of the rhythmic motor movements, the kind of esthethalin stereopathies that they. Most children who are young, about 6 to 8 months old, if you hold up a new object, the child will increase respiration and go rhythmically opening and closing. And so maybe this was just rhythmic stereopathies and a little bit more of it because the children were exposed to sign language, so the hands got massaged in some way. And so what we did is we took OptiTrack, neuroanatomical measurements of the child's movements on the hands using IrISS that went into a camera that took the, basically we built a speech spectrogram, but for sign language. It took the velocity, fundamental frequency, the velocity, the speed, the trajectory of these movements. And what we found is that differentially, when the child, within the same child, the brain honors a distinction. When the child was engaging in universal rhythmic motor movements of excitement, their feet were involved, their hands were involved, 2 hands were involved, and also the most important difference was hertz. Gestures were 3 hertz, and the 3 hertz in the child was universal to all children. But when it was linguistic babbling, it was a hertz and a half. So having seen that, we moved to the next step. We did something very bold. We had seen maturational milestones the same. We had seen structures the same. So now we went to a bold hypothesis. And the bold hypothesis was that beyond same developmental processes and beyond same mechanism, perhaps the identical brain tissue was involved. Now, this really was a bold hypothesis. And remember, in psychology, when we don't know what something is, we say it must be the same mechanism. So we had reached that heuristic in psychological science. Everybody said, well, it must be the same mechanism. So I took it one step further and said, maybe the bold hypothesis is that beyond same development, beyond same mechanism, it's the same brain tissue. Now this, we had already known. So remember, signs are of the hands and they're gestural. They should be in the right hemisphere, but they're linguistic. They should be in the left hemisphere. Which will they be? Pioneering studies by Ursula Bellugi and Helen Neville, they had already determined that sign languages were in the left hemisphere. But absolutely no one tested the hypothesis about whether the representation, whether the tissue used was identical. That was considered the area no one would go in. It was considered impossible. The tissue that is responsible for our segmentation of speech and the ability for us to see rhythmic undulating patterns that we extract from language is considered unimodal sound processing tissue. For 125 years, the tissue was considered to be exclusively the bastion of the processing of sound. I'm talking about the superior temporal gyrus. I'll get there in a moment. So what we did is we put profoundly deaf people into brain scanners. This is a very rich and complex study. It's cross-linguistic. We had English people exposed to English. We had deaf people exposed to ASL. We had French people exposed to French. And we had culturally French exposed to LSQ. And so it's 2 languages, 4 languages, 2 modalities. So we put the people in the scanner and we gave them, again, to stack the deck against us, we gave them units in sign language that are phonologically based. And so look at this box here. This is the equivalent in sign language of meaningless phonetic units. This is like I'm saying ba, pa, ta, ka, da, pa. Now, if I said that to you and I presently had you in a brain scanner, we would recruit your left hemisphere superior temporal gyrus. This is uncontroversial. It's uncontroversial that the left hemisphere superior temporal gyrus is the bastion of the segmentation, of phonological segmentation in the human brain. However, this tissue, for 125 years, was thought to be unimodal sound processing tissue. And what did we find? That when deaf people looked at phonetic units, and only phonetic units, so not gestures, but when they looked at phonetic units that had the right rhythmic temporal patterning of about a hertz, this is a hertz and a half, we can turn on this tissue like a light switch. So what we were getting was superior temporal gyrus activation, phonological tissue activation in brains that could not hear. Then we went a step further. We did a morphometry study where we looked at the density of the gray matter and white matter in the human brain. The gray matter is the cortical afferentation, and the white matter is the tracts of tissue that connect the fundamental auditory cortex to other tracts in the brain. So we took the brains of hearing and deaf people and we scrambled them. Then we flipped the x-axis and we didn't even know what hemisphere we were in. Then we did a voxel by voxel analysis of the volume of the gray matter and the volume of the white matter, and there were no difference between the groups. That means that the order to primary Heschel's gyrus and secondary superior temporal gyrus tissue that is thought to be unimodal sound processing tissue in a deaf brain getting no sound was alive and well. Why was it alive and well? Because we were wrong. The tissue is not set for sound. It's not unimotor processing tissue. Instead, it's tissue that's set for highly select rhythmic temporal patterns at the nucleus of natural language structure. What we on the outside call phonological syllabic structure, the human brain has tissue that is dedicated to find those units in the input, be it on the hands or on the tongue, because it's not doing it on sound. Speech is not special. It's doing it on highly honed temporal patterning that allows it to crack into the signal and find the units. And as I said, this is the same tissue that lets a child see that two languages are different from the get-go. And you'll see that in the next set of studies. So the biological conclusions is that speech was not special, that specific patterns were critical and special in the species, and that the importance of early language exposure is very important. So I'm just going to wrap up this part and tell you what we now know. So we now know that this is really how a child in the early life begins to learn language. This is the booster rocket, what launches the child in. We used to think that the child hears sounds, that it floods over the motor cortex, that projections are mature from the motor cortex to the mouth, and that the time it takes for those projections to become stabilized is the time it takes for us to see the child say the first babble, the first word, etc. So that this was the way it was thought to be. We now know that this is not true. There are specialized neural substrates in the human brain. What's a neural substrate? Think car parts. You open up the hood, there's a carburetor, there's a motor, there's all kinds of things under the hood. Each one has a special function. And you can't do without any of the functions. You need to have them all. But each one does a specific job. So we have a variety of neural substrates in the human brain that contribute to the child's launching of human language. We know that in these we know that there is at least 3. There's actually more. We know that the superior temporal gyrus, with this tissue, the child can discover phonological patterns and phonetic patterns. With this tissue, the left inferior frontal cortex, which is another swatch of tissue, you'll see this again in a moment. This tissue allows the child to find morphological and semantic lexical meanings. And the Broca's tissue allows the child to discover aspects of the patterning of language at the sentential level. These are booster rockets. The child's not going to learn language without input. But these are biological booster rockets. They're predispositions that sets the child in the right attentional space to be sensitive to very specific types of information in the environment at very specific times in development to pull out this information. This is the tissue that lets the child discover the units over which, at 8 months, they will do their statistical learning and the patterns. But the field had no mechanism to understand, no idea to understand where the child gets the units in the first place. And we now understand how that happens. But in the biological conclusions that I gave you before, there was one other thing that reared its head throughout all these studies. And that was this. This was an accidental finding. This was a finding that mono and bilingual children, their acquisition was developmentally similar. Why was this an accidental finding? Because there I was pairing children who were hearing, who were getting bilingualism with spoken and sign language. And so I had to compare them to controls. These were kids who were getting French and English, Spanish and English, etc. Various permutations of children. My children in my studies were achieving language equivalently on equivalent timetable. The field at large was not saying that. The field at large in this was just extremely paradoxical. And I have seen the paradoxical views of bilingualism persist. In the field, pendulum would swing between bilingualism hurts the child and bilingualism helps the child. Field would swing between bilingualism is cognitively taxing to bilingualism is linguistically empowering. The field swung between the child who learns 2 languages is disadvantaged versus the child who learns 2 languages was advantaged. So I looked at the field, which was in such a disarray, and I said, okay, we're going to take that and we're going to turn it into biological hypotheses that we will test. So the first question I asked myself is bilingual language acquisition harmful? This is what the pendulum was swinging back and forth. But come along with me on this. What does it mean if it's harmful? If bilingualism is harmful, from the perspective of the human brain, it would obligatorily mean that monolingualism is normal. And the question is early bilingual development abnormal? That was it. So this is a testable question, and we can ask this question. So I'm going to go through very quickly a series of findings. The first thing we found is that bilingual children had the same milestones. So the child exposed to French and English, for example, it hit every single milestone on the same timetable as the other language, and overall on the same timetable as monolinguals. And we can talk about why you might have this sensation, which is an accurate sensation, oh, that my child won't speak French to his grandmother, but I know he knows it. These are sociolinguistic settings of language in context with regard to language dominance and language preference, but it's not a biological capacity. We see a brutal equality in the child's achievement of maturational milestones. And this is brain-based. Whenever you see that kind of rigidity in the maturation, we immediately suspect whatever the target behavior is, it's under biological control. The next thing we saw is that the word meanings between bilingual children, a Spanish and English child, a French and English child, etc., their meanings were equivalent. It wasn't like if the child had a word in French, they absolutely wouldn't have it in English. They had equivalent meanings, they had translation equivalence, and it actually was much higher than the discipline had ever reported. We saw that the bilingual children do mix their languages, but the mixing wasn't them being confused. The mixing was highly rule-governed. They didn't violate the host language or the new language. They kept the constructions. Where they mixed was out of the syntactic clause or out of the syntactic organization. Like in French you say tableau rouge, and that would never be violated. The mixing would be outside of that canonical word order and pairing. And the mixing was sociolinguistic set by the mixing of the parent. High mixing parents had high mixing kids, but it wasn't that they were confused. The nature of the mixing was highly systematic, highly rule-governed. All right, so what we were finding is that the children, the birth bilinguals and under age 5 were, by this point I'm publishing and the field's interacting and we're having much debate in the field. So now the field says, okay, we believe, we accept a young child who's exposed early to 2 languages, multilingual children. If it's early in life, they will hit the maturational milestones on the same timetable. Now the child arrives at school, and all the myths and all the views reemerge. Now don't expose the child to 2 reading systems because they'll be confused. Before it was don't expose the child to 2 languages because they'll be confused. So now the field is beginning to evolve and accept that early bilingual exposure has the child develop in parallel ways. But then the controversy exploded at the age 5 when they arrived at school. So now all the issues got reemerged again. Children, you shouldn't expose them to 2 reading systems, etc. And so what we see, I'll go through a series of these studies. So the early myths about bilingual education truly weren't supported. We looked at early dual reading instruction and found that it does not hurt reading success. In fact, it's the reverse, and I'll go through this very briefly. I do want to convey where did these views in school come from. One of the classic ways in which they had entered the school was inspired from psychological learning theory. And this was a notion of time on task. In educational and educational policy, there was this notion borrowed from psychology and learning theory that the child has to spend a lot of time on a task and really get to know that task well, and then be allowed, when it's safe, to be exposed to the other task. And this, in learning theory, for those of you in psychology, this was mass learning, where children were first exposed to an L1, followed in time by L2. All right, and this was mass versus space learning. And if you're in learning theory or in psychology, you know that children learn better from space learning, not mass learning. Mass learning would be like students, I see some of you back there, if you cram for an exam. When your exam's done, you don't remember as much. But had you started 4 weeks ago and studied space through, you would know that, and probably for a long time after the exam. However, inspired from these learning theories, they applied this to educational policy. And in the United States, they set up two very strong systems. One is called 50-50 and one's 90-10. And 90-10 is truly massed learning. The child is put 90% of their time and grades, grade 1, 2, 3, only in English, for example. And then when it's safe, allowed to be exposed to Spanish when it won't hurt the acquisition of the majority language English. Several states around the United States had begun to experiment with what was called 50-50, and this is exposing a child to 2 languages in school from the get-go when they come in, and it's 50%. Roughly 50% of the day is in one language by native speakers and 50% of the day is another language by native speakers. The key is that it's exposure to 2 languages early in life and within the same developmental period. And that's very important. And what we found is that these children, I just took one measure to show you, that an early predicting of reading success is, we know, the phoneme awareness tasks. And children who were in the 50-50 programs were outperforming children who were monolingual children. And they were outperforming the children who were the 90-10 sequential programs. So this was very unexpected. These are a variety of studies. We also then compared children who were first exposed to 2 languages from birth, then exposed at age 3 to 2 languages. So they were monolingual from birth to age 3, and then got their new other language, or they were monolingual from birth and then got their new other language at age 5, age 7 to 9, and age 9 to 12. And so, for example, these might be children who've moved from other countries. So there might be a family where they spoke Russian in Russia, then they moved to Quebec, and they were being exposed to French for the first time at age 3. And so we compared what was the optimal mechanism to get a child into learning the other language most quickly. And we varied schools and contexts that were using where it was the new exposure to the language was only in the home and not in the school, intensive community involving also the home, or restricted classroom instruction. And this is actually quite real in the province of Quebec. It is against the law to expose a French child to English until grade 4 and only 2 hours a week. So we tested this hypothesis. This is absolutely true. Against the law. We have language police and language laws. And we tested this with many language pairings, and I know you can tell me the answer. The results was earlier is better, but what was exciting is that the brain was forgiving. The child didn't have to be exposed to language from birth. The child could be the home environment and the intensive community together combined to give children such a boost that they were able to get into the language with very good competency and quickly. The worst, of course, was the restricted classroom, the 2 hours a week in English when you were from birth to grade 4, which means around 10 or 11, get your first exposure to English. So what we saw as a summary, that the children who were exposed to 2 languages are not delayed and confused. We found evidence of new language benefits, new reading benefits, and actually converging through all these studies came a kind of optimal formula for making a bilingual child. One had to do with systematic language input from multiple speakers. Another was home and community exposure, intensive rich home and community exposure, that it did involve the school, but that critically wasn't only the school. Also, vitally important is the child cohort. So if you have children and you want the child to learn a target language, it's very, very important that the children are surrounded, have access to, even in a play date, monolingual children in that language, so or fluid children in that language. And finally, across semantically rich in multiple contexts. So this is in addition to what people had been broadly talking about, a cognitive advantage. This was specifically unfolding reading and language advantages that we had never known before. All right, so now in the last few minutes of the talk, I'm going to turn to the human brain with regard to these issues. I have shown you several decades of behavioral work. And the reason that we must turn to the brain is that the hypotheses that gave rise to the behavioral work, every time you do a behavioral study, it equally supports one or the other hypothesis. There was nothing about the hypotheses and the findings that could adjudicate between these equally plausible hypotheses. But what was really cool is that the hypotheses that, for example, bilingualism hurts a child, gives rise to testable brain hypotheses. If bilingualism hurts a child, then we should see abnormal brain development relative to a monolingual child. So this provided a new insight into human development and into adjudicating these hypotheses. Also, looking at the child's brain allowed us to track the tissue that's involved in language processing very specifically over time. So we can compare, is the bilingual child's classic language tissue being engaged as we'd see in a monolingual child? So again, we can test hypotheses about hurting a child and the abnormality of giving a child two languages too early through looking at the human brain. But the problem is there was nothing available to look at an infant's brain. What we needed was to see neuroanatomical structures, the actual origins of the processing. And we needed to see how those structures related to each other in the system. We needed to see how one tissue talked to another tissue. And we needed to see the temporal dynamics of this. Nothing did that except for one piece of equipment. This is a revolutionary advance. In another 5-10 years, you will see this everywhere. This is called the near-infrared spectroscopy system. It's small. And I'll tell you some of its features. Like a functional magnetic resonance imager, it has good spatial resolution. However, it has better resolution in temporal resolution than an fMRI. And let me tell you some of the advantages. This instrument picks up oxygenation and oxygen deoxygenation, where the brain not only gains oxygen uptake, but where it lost, who it swapped with, which part of the brain it pulled the oxygen from to give it to the other. Therefore, we can see related systems, how tissue is talking to each other. The most exciting difference for me is that this is a faster measure of neuronal activity than an fMRI. An fMRI samples once every 2 seconds. This samples 10 times a second. It's a faster measure of neuronal activity than an fMRI. It's also child-friendly. In an fMRI, how many have seen an fMRI? You're strapped in, you're rolled into the donut, you can't move. This tolerates movement. You can have babies on mom's lap moving around, bouncing up and down, and be looking at which brain tissue is engaging human language for specific parts of language. Phonological properties, syntactic structures. So it's optimal. You can study infants, children, and adults. This is the first time in history we can study awake babies. When a baby is put into it's against the law of the United States to put a baby into an fMRI under 4 years old for research. You can do it only, it's against the law in Canada for under 12. It's allowed only if the child is going to die, basically, that the surgeons need a neuroanatomical map to do the surgery. For the 1 or 2 researchers that were able to study infants, they were anesthetized or they were sound asleep. This is an awake baby sitting on mom's lap looking at various stimuli. We get within hemisphere tissue activation. We can track spatial, temporal, and brain changes. And we can put ourselves, guess what, right over the superior temporal gyrus, put our probes on it, and we can watch this tissue over time. We can even see a child who's at risk for language delay before they even babble, before they utter their first word. So very briefly, let's consider now we can go another level in. We can go away from the behavioral claims and the behavioral data that were offered, and now we can look into the brain and test hypotheses of deviance and whether 2 languages hurt a brain. So the claim is that bilingual brains are deviant and disadvantaged. This is, again, resurging through, rippling through. We saw it in acquisition, we saw it in bilingual school, and now we see it in bilingual brain studies. So the first flush of brain studies said that bilingual brains are deviant, and I'll tell you why in a moment. But let's just test this hypothesis with me. If bilingualism is deviant, then again, monolingualism is normal. That implies that monolingualism has privileged neural status in the human brain. We can test this. Okay, this is a real title of a brain scanning study for bilinguals. What causes the bilingual disadvantage, the dual task analogy. Let me tell you the reasoning. This is very real. This is alive and kicking, this hypothesis. This comes right from cognitive psychology. It's cognitive psychology theories. Here we go. It's bilingualism is a complex and taxing dual task. This comes from bilingual context, overwhelms the language learner, causes interference, drains cognitive capacity, it drains central executive system, it taxes working memory, and it taxes attentional selectional inhibition processes. This is a very strong theory in neuroimaging of bilinguals. Differences here, bilingualism should be more challenging than monolingualism. But these are wonderful hypotheses because with the brain scanning equipment, we can test them. All right, an alternate hypothesis is bilingualism, instead of being complex and taxing, dual tasking, like your parallel processing, it's a complex and enhancing language processing. These render very strong theoretical, very strong neuroanatomical predictions. You could probably generate them for me. Bilinguals should use more cognitive brain tissue and less language tissue. This is a very clear, simple test of these types. So these are the hypotheses. What's a direct test of this? In the human brain, we should see more frontal lobe activity, more cognitively taxing, and we should see perhaps a attenuated engagement of language tissue. Okay, just so that we know, imagine I'm looking this way and we took this part of my brain off. Here what you're seeing is the front where your eyes would be, and the back is the back of your head. Right around the area of your ears is the left inferior, the left superior temporal gyrus, which is responsible for temporal patterning, unique to language phonology. Broca's tissue, motor sequence and segments of sounds and words and sentences, syntax. And we have the left inferior frontal cortex, which is very important for your lexicon, the search and retrieval for information about words and morphology. So here is the tissue that involves classic human language processing. And this frontal area is where we would predict, and where the field predicts there would be additional activity for if you were, if bilingualism was taxing. All right, so I'll just let you see this in a visual representation. This is the rough schematic of language in a monolingual. Then this would be what is predicted extrafrontal lobe activity, or alternatively, extra language activity, or both. But we should see a differentiation between monolinguals on the top and bilingual challenges on the bottom. That's the prediction. It would be extrafrontal. So I'm going to briefly touch 3 types of data, one from infant data, one from children's data, and one from adults' data. Let's start with the infants. And infants are really cool because infants have an amazing capacity. All human infants, your infant and Christina's infant in the room, began life with the capacity to differentiate and discriminate all of the world's phonetic units, any and all of. It's an amazing biological capacity. By 6 months of age, our species does a swap. They lose the universal capacity to discriminate the phonetic units that they were born with. In fact, it's one of the few areas in human language acquisition where the child gets worse as they grow up instead of better. So they lose the universal capacity, but nature does a swap. This is a gorgeous nature-nurture dance. Nature does a swap. Now they get increased capacity to do the fine-grained discriminations in their native language, but they've lost the ability to the non-native languages. However, if you're a bilingual child, what happens to you? Bilingual children were shown behaviorally to continue to be able to discriminate phonetic units to languages they never heard. Published in the literature, you will see claims. Failure to attenuate or close. Bilingual babies are patently called deviant because they didn't show this shift. Well, this is very interesting. The brain could give us some information on this. What we found, we did several studies on this. There were no significant differences. This is just a dramatic way to show you there were no significant differences between young babies, young bilingual babies who were discriminating between sounds in their native language, 2 languages, and monolingual babies, the sounds in their 1 language. All's well. However, the older baby is when it's processing non-native sounds like Hindi. The phonetic contrast when the oldest baby showed a greater activation in the superior temporal gyrus relative to monolinguals. So what does that tell you? What should they have shown us if they were failing to close? We should have seen greater frontal activity, and we should have not seen greater STG, superior temporal gyrus activity. Well, so in a nutshell, because I'm touching very quickly on this, all of the reference to this are at the end. The children were not disadvantaged, they were advantaged. Here's why. They did close for their 2 languages. They did stabilize on, if they were getting French and English, they closed to French and English. Where they stayed open was to new non-native languages, which means they are advantaged. These children are able to continue to differentiate non-native contrasts when the hearing child lost it. It's the hearing child whose ability is attenuating. The bilingual child is staying open to new languages. They have stabilized on the languages that they should have stabilized on so that they can go on to learn language, their individual languages. The brain demonstrates that it stays open longer to new languages, and we do see this going right up to the developmental scale. This brain-based advantage gives them, that's the explanation for why the children were able to have more phonemic awareness than the monolingual children and the sequential children. So we're seeing a marriage between the behavioral data and the brain data. And it's because the 2 languages it's like a perceptual wedge. It's holding open the auditory tissue. It's holding open the linguistic tissue. And it's preventing it from narrowing it down. The monolingual child's brain attenuates down. The bilingual child's brain stays open. I'll show you just 2 quick other examples. The discovery in a nutshell, for the older children, now they're children and they're reading. They're in grades 1, 2, and 3. The early bilingualism strengthens their reading and strengthens past other higher cognitive capacities involving math, decision-making, etc. So it's not even something that's restricted just to language or general higher cognition. We see greater language recruitment in the language, we see greater language tissue recruitment, and we don't find more frontal activity. So that's the punchline, and I'll just show you. Early exposure to 2 languages provides the brain important benefits to each language, which behaviorally we see in reading advantages across the 2 children. Monolingual children experience benefits from bilingual education, and we see this both in their brain and their behavior. This I'll just very briefly explain because I think it was an amazing, unexpected finding. We had English monolingual children from English monolingual homes. Half the children went to English monolingual schooling, and they were from the highest SES in the whole United States. These schools were the richest, from the richest schools, most affluent, extracurricular activity, parents' income, literacy in the home, etc. These were compared to very low SES children, among the lowest SES in the nation, at 98% free lunch in the school. And if you know about American low SES, that's a staggering statistic for the schools. 98% of the children, that's a very significantly high poverty level. But their English in the house, they were put into bilingual schools by accidental where they lived, and they were tested in English. These children, which they were graded for IQ, they were graded for everything. These have been published and replicated. They outperformed the children in English, on English, and outperformed them. And the children, these from the highest SES in the United States, which means the bilingual schooling was so powerful a positive effect on the child that it was able to ameliorate the deleterious effects of low SES on these terribly impoverished children. And you can read the backgrounds on these children and the backgrounds on the schools. So that was a very surprising finding. Also with the children, I'll just give you one example, which was another surprise finding. So remember that the hypothesis is that the bilingual child's brain is deviant and that it's a taxing thing to be bilingual, and you should engage more frontal lobe activity. Ironically, it was the monolingual children who engaged more frontal activity. So when bilingual and monolingual children were given irregular words and regular words, so an irregular word would be like a verb that conjugated irregularly, and a regular word would be a regular word. So like you don't say goed, you say went. So went is an irregular verb. Versus skipped that takes the regular ed. So the bilingual child pulled in the left inferior frontal cortex, which was semantic analysis tissue, and more of it. You can see this was quite low activity for the monolingual child. The monolingual child devoted huge amounts of effort to dissociate irregular and regular words. So ironically, it was the monolingual child who struggled with the task, and their brain showed it to us, and their bilingual child was actually advantaged in this. Finally, for bilingual adults, early exposure. If you have a bilingual adult, and now we're going to give them language tasks and cognitive tasks, and we're going to look at their brains in the scanner. If they were early exposed, we see the same brain areas in their 2 languages and in the classic language tissue. The only difference we see is more of the classical language areas, not less, but more, and we do not see difference in the frontal cortex at all between bilingual brains and monolingual brains. Again, this was This is now considered a citation classic in the Journal of Cognitive Neuroscience, and it's been replicated by many labs. If you had early exposure to bilingualism, you pull in the same tissue as a monolingual would pull in for language, more of the tissue. And we'll talk about that in a moment. You do not pull in more frontal lobe activity. It's not cognitively taxing to be a bilingual. It's not a dual task. It's language. If you had later exposure to your two languages, you show variable behavioral proficiency. Some people are very proficient, some people aren't. But a characteristic of later exposure is different brain areas. We see greater frontal lobe. Here it is. Now we're seeing greater frontal lobe activity. Now we're seeing more prefrontal brain activity. Now we're seeing more right hemisphere homologue. Why is that? Because it's not that you can't do it. I can go out and learn another language right now, but it will be more effortful. I'll make more errors. No native would look at me and say, oh, you're a native speaker of Japanese. Because those early roots that were available to me have stabilized. And now the brain has to get to the same outcome through a different route. And now it will go through your frontal lobe, where you will solve aspects of this language like a crossword puzzle or relation, or you will be translating. This is the greater frontal lobe activity you see is translation. It's more of, we also see the precuneus, which is also indicative of when you're translating between your languages. So rather than seeing this, we find this. There's a greater extent and variability of a bilingual to use language tissue. So the hypothesis that monolingual is normal and the initial state, we have no evidence for that. We see the identical timing and language and reading advantages. The hypothesis that the monolingual brain is neurally privileged, we see no evidence that. We see the same classic brain tissues. The brain and behavior differences exist between a monolingual and bilingual. A bilingual does have the greater use of the extent and variability of language tissue, but the differences do not mean they're deviant. In fact, it means that the bilingual is getting neurologically and behaviorally advantaged. So I have a way to look at this. When a monolingual is being raised and not exposed to multiple languages, as you saw with phonetic discrimination, the child's ability attenuates. We also see that when a monolingual is born and they're not exposed to multiple languages, their language faculty attenuate down to the left hemisphere. So it's almost as if a monolingual brain is like a brain on a diet. It's on a very tight diet, where the bilingual language experience reveals to us the outermost limits that human language processing brain tissue could assume if only it had the good fortune of being exposed to two languages. Okay, so very briefly, the practical implications, policy implications of this. First, I would say that I've summarized 43 years of research, and I think we can now, I feel confident saying, remove discriminatory practices, do not withhold early multilingual instruction from children. Early bilingual or multilingual language exposure and gives bilingual language, bilingual reading, higher cognition advantages that last the lifespan, and as I know some of you heard, also protect you from Alzheimer's disease. And we know why. We know we know exactly why. I could talk to you at a break as to why it protects your brain. It stops apoptosis. It stops cell death. Require research findings to be available to parents. Require research findings to be available to medical practitioners, clinicians, teachers, and policymakers. So the significance of this is that processing both languages or multi-languages from early life provides stunning language, reading, and higher cognitive advantages for life. And that is the brain and behavior foundation of the bilingual advantage. I want to leave you with a few things. Merci, grazie, dear Gwit, and thank you.